Okay, welcome. Is everybody excited to be here at First Championships? Yeah, me too. And I'm excited to share with you 4 different NASA missions. These NASA missions go to small bodies across our solar system, and don't worry, I'll explain what that means. So these small bodies, they're asteroids, comets, small bodies in the outer solar system, icy things like Kuiper Belt objects, for those of you who are so somebody can't hear me in the back. Let me try moving this a little closer. So they're small bodies like Kuiper Belt objects that are icy, cold bodies in the outer solar system. So we're going to take a tour of missions from a near-Earth asteroid to a main belt asteroid to a Trojan asteroid, which orbits with Jupiter, all the way out to the outer solar system with Kuiper Belt objects. But before I tell you about the missions, I want to tell you why NASA cares about small bodies. Why do we have a bunch of missions going to these populations of objects? And it amounts to, there we go, that's going to work better. It amounts to wanting to understand solar system evolution and formation. So about 4.6 billion years ago, our solar system was formed. It was formed from the gravitational collapse of a large giant molecular cloud. Our sun formed in the middle, and then the gas and the dust around it collapsed into a disk. And in that disk, the dust and the gas combined, and they started to accrete. Hi, you guys. Welcome. Feel free to move your chairs over here so that you can see better. So if you want, you want to be able to see the screen. All right. So that protoplanetary disk, the disk that existed after the solar system just first started forming, that's where all the action happened. That's where our planets came from. That's where these asteroids and comets came from. So we want to understand how that process worked. But once the solar system started forming 4.6 billion years ago, it wasn't over. There was still lots of activity that happened. There were collisions, and now we believe that there was something called giant planet migration. And I'm going to explain that. It's a little complicated, so I'm going to start with a diagram and a model. This is called the Nice model. It's called the Nice model because people came up with it in Nice, France. And these orbits shown here are the orbits of the giant planets: Jupiter, Saturn, Uranus, and Neptune. And out beyond the giant planets is a disk of frozen, icy small worlds called Kuiper Belt objects. They're named after a scientist named Gerard Kuiper, who was one of the first people to predict that they existed. And so we believe when the solar system formed, it looked something like this. There were a bunch of giant planets, and there were objects out in the Kuiper Belt, these small objects. There were also the terrestrial planets that I don't show in this graph because they're near the sun, and their gravity wasn't strong enough to really participate strongly in what I'm going to show you, this giant planet migration. So what happened was that the gas drag from the protoplanetary disk caused an exchange of angular momentum, and that's what makes the giant planets migrate out. So basically there was an exchange of energy and angular momentum. And I'll show that again in a minute, but let me just explain a little more what was happening. As the planets moved out in their orbits, it came to a point where Jupiter would go around 2 times for every 1 time that Saturn went around. And when they hit that commensurability, when you hit the 2-to-1 resonance, as we call it, when Jupiter's going around twice compared to once for Saturn, that means that then every time Jupiter and Saturn are in that location, they're getting an impulse from each other, and it's additive. And that additive impulse caused the chaos that you saw in this animation. This is a model of what was happening in the solar system. So you can see the orbits are moving. You can see the orbits are getting slightly larger. The number of green dots is decreasing. And then all of a sudden it just goes crazy, just kabloom. And this happened approximately 800 million years after the solar system formed. Now, you might think that's crazy. How can we know that? Why do we think that's true? Well, that NICE model of solar system evolution explains a lot of observables in our solar system. I'm a scientist. I look at the data, I look at the evidence, I try and come up with theories and models that explain what we see. And all the other models of solar system formation had many more Kuiper Belt objects than we see today. It also couldn't explain how we got Trojan asteroids, and I'll explain what those are in a minute. And it also became really confusing when we got the Apollo moon rocks back. We got the rocks back from the Apollo missions, and it showed that a lot of the craters on the moon were formed about 3.8 billion years ago. And you might remember that I said that the solar system formed 4.6. Well, what can explain why we have a massive influx of impactors on the moon and likely on the Earth 800 million years after the formation of the solar system? It is exactly the NICE model that can explain that. But this model is not fully proven yet. We don't know if it's really true. It's just one thing that explains the data that we have. So that's part of the reason why we have these missions, so that we can better understand not only system evolution, but the solar system formation. So now I'm going to tell you a little bit about each of the missions and how that ties back into either formation or evolution. First, there's the OSIRIS-REx mission, and it's going to a near-Earth asteroid. There's many different types of near-Earth asteroids. Some orbit just between the sun and the Earth. Others cross the orbit of the Earth. And others just come near the orbit over the Earth, but are outside of Earth's 1 AU, which is the distance between the sun and the Earth. So there's many different kinds, and we know that there's more than 15,000 near-Earth objects. And in fact, NASA has a number of programs going on right now to search for these near-Earth objects. We search for objects because we want to know if something's going to come by and impact the Earth. And in fact, in the news, you might have heard on Sunday that there was a football field-sized object that flew between the Earth and the moon, and we had only discovered it the day before. And it was picked up from one of those surveys that was looking for near-Earth objects. In reality, we like to find them much earlier, but it's hard. They're small and they're dark. So this is a particular class of object that we're interested in for many reasons. And the OSIRIS-REx mission is going to go target one particular near-Earth asteroid. That one is named Bennu. And you can see right here, this is a radar image taken at Arecibo Observatory of Bennu. So there's a big radar dish in Puerto Rico, and it radiates energy out into the solar system, in this case, out towards Bennu. And then this is the reflection of the radar that we get back. And from this data, we were able to produce a shape model for Bennu. It looks like this. And part of the reason we want to go to Bennu is because it's a sample of a primitive asteroid. We can tell that by its spectral type. So if you spread the light out into the different wavelengths, we can see that it's what we call a C-class asteroid, which means that it's primitive. And that means that it's telling us it's a relic from the solar system formation. And this is going to be really interesting to study. And I want to tell you about how big it is, because it is approximately the size of the building we're in now. I don't know if any of you recognize this. This is the layout for FRC. Here are all the fields, and those are the pits. And this is the layout of the FRC fields relative to the size of Bennu. So these are 2 scale. So this is a very small object, but it could do a lot of damage if it were to impact the Earth. And in fact, in the 22nd century, there's a 1 in 2,700 chance that Bennu would hit the Earth. It's very unlikely, but that's part of the reason we want to study it. How do you learn about these objects? How would we possibly do something about it if an object was going to hit the Earth? What are the surface properties like? If we look at Bennu and if we try and push it, would it just crumble, or how solid is it? These are all questions that we want to know about near-Earth asteroids. And so the mission OSIRIS-REx, you see an animation here, is going to go and sample Bennu. This is the sampling arm right here. It's called TAG-SAM, and it's on a long boom from the spacecraft. The spacecraft will go down and just touch the surface. And you're going to see an experiment that was done on a zero-G airplane, here it is, of the sampling mechanism. And then this is simulant of what the surface on the near-Earth asteroid might look like. And what happens is nitrogen gas, and an inert gas, is shot into the dirt to kind of agitate it so that it can be collected into the sampling head. And then it gets put into this capsule. The sample gets put into this pristine capsule. The spacecraft is going to head back to Earth and then eject this capsule so that it'll land on Earth, and we'll be able to have our first ever sample retrieved from a spacecraft of a near-Earth asteroid. And I couldn't help but try and make an analogy to FIRST. So my analogy is it's like picking up power cubes in FRC. So there's many ways to pick up the power cubes in the FRC game. You need to pick them up and deliver them either to the switch or scale. And you can see lots of different teams came up with different ways of doing it. That same brainstorming and thought process and engineering and iteration that you guys do in your FLL, FTC, or FRC robots is the same process that the engineers on OSIRIS-REx went through to understand how to best sample the surface of Bennu. So next, I'm going to move on to the Psyche mission. Psyche is a mission to the asteroid belt. This is the main belt of asteroids located between Mars and Jupiter. It's probably the one that you learned about in school. It's estimated that there are 1 to 2 million asteroids greater than 1 kilometer in size in the asteroid belt. We don't know of all of them yet. That's our estimate. We're still trying to observe and find all of them. So, and the asteroid belt is the white dots here given in this schematic. So you have the sun, and then the terrestrial planets, Mercury, Venus, Earth, and Mars, the asteroid belt, and then Jupiter, and later I'll talk about the Trojans. So despite what this graph looks like and what you've seen in science fiction movies, the asteroid belt is not really dense. Objects are very far apart in the asteroid belt. But that object that the Psyche mission is going to go see is a main belt asteroid called Psyche. And Psyche is a really interesting object because it's metallic. It has a density of 5 to 6 grams per centimeter cubed. So that's much denser than most asteroids. It's denser than many different things. It's kind of dense like the core of our Earth. But there's really no good way to sample the core of our Earth. We can't go down there. Of course, we use seismic waves to understand as much as we can. But this mission is going to go and visit this nickel iron core that we think was the core of an early planet that got disrupted in that formation and collision experience that I showed you in the formation and evolution of the solar system. So this is a way of looking at the interior of those planetesimals, the things that were the building blocks to our planets. and it offers a unique way to look at the collisional history of the solar system. And for scale, I wanted to let you know how big these objects are. Psyche is about 200 kilometers across. Note that I'm using metric units. I know probably the audience likes to think in English units. As a scientist and engineer, I try and think in metric units, so I'm going to challenge you guys to start thinking that way. But Psyche could fit in between Houston and San Antonio in Texas. So any of you who are from Texas or had to drive that area, now you have an idea of how big Psyche is. Now, the Psyche mission uses something called solar electric propulsion, and that is a way of ionizing xenon gas and emitting it to get more thrust, basically, than chemical propulsion. But that requires a lot of power. And in fact, they use solar power for the spacecraft, like many spacecraft do, but they can generate up to 20 kilowatts of power. And it's very high voltage. It's probably 300 to up to 1,000 volts for that solar electric propulsion. And just wanted to make a comparison to what people are working with in this room. The FRC batteries have about 12 volts, and many batteries do. So we're talking about very different power source here. Next, I'm going to talk about the Lucy mission. The Lucy mission is going to Trojan asteroids. And unlike the main belt, you guys probably didn't learn about Trojan asteroids in school. Did anybody learn about Trojan asteroids? Raise your hand. Oh, good. Yeah, all right. Excellent. I'm excited about that. I'm the deputy principal investigator on the Lucy mission. And so I find myself often explaining what Trojan asteroids are. They're asteroids that orbit in the same orbit as Jupiter, but they are 60 degrees ahead and 60 degrees behind Jupiter. In this diagram, this is Jupiter, Mars, Earth, Venus, and Mercury, and these are the Trojan swarms. There's 2 clouds of objects. These are located at Lagrange points. These are stability zones where if you put an object here, it tends to be stable and will not deviate from this location. It will orbit in this area around the Lagrange point, but it doesn't escape, say, and hit Earth like the near-Earth asteroids could. So there's thousands of known objects in the Lagrange points of Jupiter, almost 5,000 on one side and about 2,500 on the other side. And there's many more objects that we don't know about today. So the Lucy mission has a goal to sample the diversity of the Trojan population. And the reason we want to sample the diversity is because these objects in the Trojan's clouds, they look different from each other. There's red ones and less red ones, and they have different spectral types. And we can't, the methods, earlier models of solar system formation and evolution couldn't explain how you could get different types of objects in that same area. But the NEISS model explains it pretty well. And you see the little animation down here. I'll start it, there you go, it starts again. The giant planets kind of move around and they clear out this zone where the icy bodies used to be in the outer solar system, and some of them get trapped here. And if they're closer in, they're likely more gray, and if they're further out, they're more red. And that's how, see the different gray, yellow, red, and that's how we end up with Trojan population that's so different in color from each other. And that's one of the things that the Lucy mission is going to go and try and understand. So we're going to do a flyby of 6 different Trojans. We launch from Earth in 2021. We do Earth gravity assist the next year to pump up our energy to increase our aphelion, so we're going out further. Then we do another Earth flyby, and then we fly by this main belt asteroid, Donald Johanson. It's just a bonus. It's something that we happen to be able to fly past. We're going to exercise the spacecraft there. When we found that we flew past this object, it didn't even have a name. So we named it Donald Johanson after the anthropologist who discovered the Lucy fossil, the Lucy hominid fossil. And that fossil is what the Lucy mission is named after. We wanted to name the mission after the Australopithecus fossil because that fossil changed the way we understood human evolution, just like the Lucy mission is going to understand or transform the way we understand solar system evolution. So we fly by Donald Johanson, and then we keep going out, and we're going further and further, and finally get to the orbit of Jupiter right here. And we fly by Eurybates, Polymele, Lucas, and Orus. Those are just 4 Trojan asteroids that we chose because they're different colors, they have different sizes, and we're able to sample the diversity by doing that. And then we're going to swing back by Earth again. This will allow us to target our last flyby. The last flyby will be in the year 2034, so you guys can all figure out how old you'll be. You'll be well into your careers by then, probably. And it will fly past this object called Patroclus. Now, Patroclus isn't just one object, it's actually a binary pair. It's 2 equal mass, equal size objects, Patroclus and Menecius, and they orbit the same center of mass. Now this is just an artist's rendition of what it looks like. And this is a sample of data taken from the Keck Observatory with their adaptive optics program. Now this is colorized. They don't look orange like this. If you look at Keck, that's just the way the data was presented. So this is going to be a really interesting object to observe because its binary nature hints that it is very primitive. It wouldn't take much energy to strip those 2 objects away from each other. And so we're going to visit this because it's a very primitive object, and it's going to help us understand the solar system and evolution. And I wanted to tie in the center of mass to the center of the scale, which some of you have been thinking about a lot, and how the scale tips depending on which side has more mass. And that's the exact same physics that's happening in the Patroclus-Menecius orbit and determining the center of mass between the 2. Now, the last mission I want to talk about is the New Horizons mission. The New Horizons mission is the mission that went past Pluto. Hold on. Interesting, I didn't expect the sound to run, but we'll just ignore that. So New Horizons brought you this picture of Pluto, and there's some over there if you would like it. And these are the objects that are out past Pluto. And these objects are the remnants of solar system formation. And we've been searching for another object to travel to. And in 2014, we found one. It's called Ultima Thule. That's its nickname for now. It doesn't have a permanent name. It was discovered in 2014. And in fact, these are the discovery images. You can see 5 images. They're stacked on top of each other with Ultima Thule circled here, so you could see how it was moving across the sky relative to stars in the background. So this is a small object. It's so small, in fact, it's never been seen with an Earth-based telescope. The only telescope we've ever been able to observe it with is the Hubble Space Telescope. And so we think it's about 30 kilometers in diameter. It's dark and it's red, and its orbit indicates that it's one of those very primitive objects left over from solar system formation. And so we're going to fly by this object on January 1st, 2019. We don't know, we have indication that it's either what we call a contact binary, where it's 2 objects stuck together, or it could be a binary object like Patroclus and Menecius. And we don't know, and we won't know probably until we get there. We have an autonomous mode, and I couldn't help but show the autonomous mode of FLL when I'm talking about this. We have a special autonomous mode on the spacecraft where the spacecraft can restart in case something goes wrong, because it takes 12 hours to get the signal to go to the spacecraft and then back. So our autonomous mode, our special autonomous mode, is going to last from Christmas Day this year till January 3rd. So you can look forward to hearing about that in the news. So I'm also an FLL coach, and so I know how hard it is to get this all to work. And I wanted to share with you just a graphic of our timeline for New Horizons of about a day and a half across our closest approach. I don't expect you guys to be able to read this, but every dot and line on here is a different activity. Each line is a different, each instrument is a different color, and so we're doing things with many different instruments, sometimes simultaneously, all in autonomous mode. And I wanted to talk about teamwork, because teamwork is essential. Teamwork is essential on NASA missions. You cannot get a spacecraft to function properly without project managers, administrative staff, engineers, scientists. We need graphic artists, machinists, and drafting people. We need all different types of people to be able to make a spacecraft mission successful. And you've probably seen in your FLL team or your FTC team or your FRC team that it takes all kinds to pull things together. You might have people who do software or hardware or control systems, maybe your chairman's team, your chairman's presenters, your outreach, your business team. It takes all kinds to run a big mission, like a NASA mission, or to run a successful FIRST team. And these are the skills that you guys are learning in FIRST. So I'm looking forward to the New Horizons encounter with Ultima Thule on January 1st. We don't know what we'll see, but I hope that you guys tune in. You can go to our website right here, pluto.jhuapl.edu. The encounter is just 30 minutes after midnight on Eastern time. So it's going to be pretty exciting. Hopefully you'll see it in the news, and you can spend New Year's with NASA, exploring the outer solar system. Thank you. Any questions? Oh, that's awesome. It was totally understood. Coy? How close do the spacecrafts get to the objects? So for Bennu, it gets just on the order of meters away. But New Horizons will be flying 3,500 kilometers from Ultima Thule, if all goes well. As you remember, I said we don't know much about the object, and so we don't know if there's hazards in the environment. So we're planning 2 flybys, one with the closest approach distance of 3,500 kilometers, and the other one with 10,000 kilometers. Both will return great science, but the 3,500 kilometer ones will have much better images than the other one. So hopefully there's no hazards in the way and we can manage to get the data. For Lucy, our nominal flyby distance is 1,000 kilometers. The smallest object we fly by, though, Palomili, we want to get its density. And you get its mass. To get its density, you need the mass and the volume. To get the mass, you have to measure the Doppler shift. So the shift in the radio signal from the spacecraft as it's going by, the acceleration of the spacecraft due to the body. And Palomili is so small that in order to be able to do that, we'll be flying by about 300 kilometers from the center of the surface. Yep. Yeah, so New Horizons, the question is what instruments do we use to monitor the activity in autonomous mode on New Horizons? So it's not only the payload instruments, which are cameras. We'll have cameras, but it's mainly telemetry. So we have voltages and current monitors all across the spacecraft, and we will be looking at if something has pulls more current than it should. We also can tell if the computer can't keep up with the number of commands it's trying to execute. So there's mainly telemetry signals in the system. We've got temperature, we got thermistors, which are temperature measurements, all sorts of measurements on the spacecraft like that. Mm-hmm. So it depends on what it's measuring, basically. The spacecraft, the prime functions of the spacecraft are the most have the least tolerance. But the instruments, it depends, like the infrared camera really has to be very cold. But we'll still take data, even if something happens and it made it warm, because we're flying by, we're not gonna stop and go into orbit. And so the tolerance on the temperature that we can accommodate, it's probably about 15 degrees Kelvin, but we'd still take data. But with the current and voltage, that's a little different. And we have readings that are very accurate, but there's a wide range of operating currents and voltages. So we have about a 3-volt band that we can operate in as far as voltage. Anybody else? Mm-hmm. So what happens to New Horizons after the mission's complete? That's a good question. So we're in our extended mission now, because our first mission went to Pluto. Then we wrote a proposal and got accepted to do an extended mission to this object and take distance observations of other Kuiper Belt objects. It's gonna take even longer than it took for Pluto to get the data down. We think it's gonna take 22 months to get all the data down from this. But at that point, the mission would be over. We will write another extended mission proposal and continue observing. I don't know if we're going to be able to have a flyby of something like this, because we haven't identified another target that we're going near. But we have plasma instruments on board, we have radio science instruments on board, we have a UV spectrometer on board. All of those are useful instruments, even if we're not flying near a target. So much like the Voyager spacecraft is still operating out in the outer reaches of the solar system, that's what I expect New Horizons will be doing. Or I should say, that's what I hope. Anybody else? Yeah. Yeah, so what are the costs of the missions? So Lucy and Psyche are what's called Discovery class missions, and that's the relatively small spacecraft, planetary spacecraft size. Even though I just said relatively small, it is about $450 million for development, okay? The other missions are closer to $1 billion. Any other comment, question? So one thing you should know about that, sometimes people hear those numbers and they are huge, but all of that money is spent here on Earth. It's spent on engineers and machinists and draftsmen and project managers. So it's going back into our economy, and it's keeping our technology at a high level so that we can continue to do these types of things. Mm-hmm. Sorry, go ahead. Yeah, so the instruments, depending on the instrument, they can be between about 15 million and 60 million, ballpark, and the rest of it is the spacecraft. And you know, and of course, your testing, your design, your testing, and but the design and testing is all wrapped into those instrument numbers. Sorry, go ahead. Yeah, so none of these spacecraft are going to come back. The New Horizons spacecraft doesn't have enough energy to come back. It's going out, and it's never going to come back into the inner solar system. It's just going to keep going, much like the Voyager spacecraft. The Lucy spacecraft will just keep looping around the solar system, much like you might remember the Cassini spacecraft was plunged into Saturn. Ultimately, that'll probably be the fate of many of, not Saturn, but maybe Psyche will land on Psyche, that kind of thing. Yeah, so the question is, in the future, will we have reusable spacecraft? That would be great. Right now, everyone is uniquely made for the reasons that you're using it, and so you couldn't reuse it. And in fact, when I started my career in the late 80s, early 90s, there was a big push called smaller, better, cheaper, and NASA wanted to make one spacecraft bus to use for everything, and I worked on that program. And before long, they realized that wasn't possible, and they canceled. They were going to build CRAF, which was going to a comet rendezvous asteroid flyby, and they were going to build Cassini. And they realized that it just wasn't realistic to do that. They canceled CRAF, and Cassini became Cassini, which is awesome. But they have tried that experiment, and we're just not there technically yet. And also, you need to be able to have enough propulsion to launch it where you need it to go, and a lot of that comes from the launch vehicle. Mm-hmm. Yes. That's one of the things they do. And some of those other animations that I showed, the one with the discovery images, that's actually discovery data, but it took a real artist's eye to put that together in a way that conveyed the information. Often when we have press releases, there's images there that you've got the real data, but then you've also got some sort of explanation in a drawing by a graphic artist. We also employ graphic artists a lot on our proposals. You need to be able to give the review team something they can really see, this is what it's going to look like. And so there's a lot of need for graphic artists. Mm-hmm. Over the last, say, 20 years, how much more effective and efficient have spacecraft become? The real one really strong way to look at that is to compare Voyager with New Horizons. The Voyager spacecraft, if you ever get a chance to go to the National Air and Space Museum, the Voyager spacecraft and the New Horizons spacecraft are hanging together in one room. And you can see the size of New Horizons is much smaller. It was advances in technology that allowed it to be smaller, which helped save money. And we have better technology. The Voyager spacecraft had Vidicon imagers, which I know probably doesn't mean anything to you guys, but they're very old and they didn't have very good resolution. Whereas the New Horizons cameras are charge-coupled devices, and so the image quality is much better. So there's all sorts of different ways. The power use went down, the power efficiency and the power delivery systems have gone up, the size of the instruments have gone down, the resolution is improved both spatially and spectrally, so if you're looking in wavelength at a spectrum, we got much better resolution there. So it's, I would say, 1 or 2 orders of magnitude, probably 2 orders of magnitude across most metrics that you could think of. One last question, if anybody has any. Sure. So what information would we get from physical samples? Yeah. I would love to be able to have a sample return, say, from Pluto or a Kuiper Belt object. That would be outstanding. And in the future, I'm sure we will, but it's going to be a long ways off. So this is Pluto right here. And this part right there, That's a large nitrogen glacier on Pluto. I would love to be able to sample that. I don't even need to return it. I want to understand the rheology, the way that that surface reacts to stress and strain, so they can better understand the geology and what we see going on Pluto. So a lander would be outstanding, and that would be what I would want to do. All right. Well, thank you all for coming. And if you want pictures or stickers or bookmarks, help yourself over there.